Good morning, everyone. Thank you for joining our webinar. We will go ahead and get started in just a couple seconds. All right, good morning. Thank you very much for joining our webinar this morning. My name is Corey Carlson. I am responsible for sales for Eurotech Holdings, and we are excited about our webinar today. We have a partnership, which we'll explain a little more detail here soon, with Inversa. And as the title of our webinar is, Taking the Guessing Game Out of Asset Management. And we have had this webinar or similar version of this probably about 6 months ago, and really we wanted to have it again for a couple reasons. One, as the partnership has evolved and we continue to meet with different DOTs, municipalities, engineering firms, we're seeing a lot of interest in this technology, as well as even questions from our customers, as well as our webinar attendance is continuing to climb. We thought it would be great to basically have a webinar on Inversa again. So for some of you, it may be a repeat. We've got some new case studies we're going to share with you. But for others, it's not only is it a new webinar, but it's actually a new technology that you may not even be aware of. The thought of being able to see through pipe is pretty mind-boggling, even to myself, who's been exposed to the technology through this partnership. So before we get to Inversa, I'd like to just do a brief introduction of who we are, Eurotech Holdings. During this webinar, any questions that you have, please hit the question button, and we will have a Q&A session at the end of the webinar. So just type in the questions, and at the end we'll go through all of them. We will adjourn at noon Eastern time, but for those who've got to go, but if we want to stay later, ask questions, we'll be doing that as well. There will be one PDH credit available based on your state, so that's available for participating in this webinar, but you'll have to check with your state as far as whether it is accepted or not. So Eurotech Holdings, we are a contractor who specializes in infrastructure and commercial work, headquartered in Florida. We operate in 31 states, and really our core business is a chemical grout that we use to stabilize soil. We can increase bearing capacity of footings, stop I&I inflow and infiltration on infrastructure. But we're also involved in other trenchless sanitary and storm technologies such as Centripipe. Safety is a top priority for our company. We've got a very low EMR of 0.76 for those of you who are familiar with that number. Industry standard is 1, and so we are below that, which is a good thing. If you participate in our recent webinars and seen any of our sales engineers give lunch and learns, really our big push has been an outside and inside approach to the civil engineering market, and there's a reason for it. For many years we have all been focused on the inside of structures and pipes. It's hey, let's reline, let's do CIPP, or let's do a spray liner, let's whatever it may be. It's all about focusing on the inside of the structure, whether it's a manhole or a pipe. But what we are continuing to find in the industry is that that's not always the right solution, that it can just be a band-aid. So instead we need to actually look at the not only inside the structure but the outside. This article from 2012, Trenchless Technologies, is a perfect picture and article to describe really the situation that we have with America's infrastructure. This manhole in Chicago was relined with MS 10,000, which is 10,000 PSI, a AP and permaform product that we are an applicator for. It was relined. They thought they'd solved the problem, but then you can see the old brick manhole and the soil envelope surrounding was not stable, and it became a catastrophic failure. So the reline was done correctly in such that they could pick up the manhole and move it. So the liner worked, but the soil envelope was forgotten. So that is what really we are focused on and going after hard, is the outside as well as the inside. In addition to those examples, we've also see that I&I is a major, inflow and infiltration is a major sore spot for taxpayers as they learn more and more about it, because municipalities are spending money to treat what should be sanitary water, but instead it's actually stormwater that has gone through the leaks and cracks of pipe. We had a January webinar with George Kurz, who did a third-party study on the state of Tennessee. And as you can see by the graphs, what has been circled and pointed out is you can see that the flow was affected by the wet season and rainfall. This study covered 155 different municipal systems, and the research showed that 44% of the sanitary flow in Tennessee was actually stormwater. It was actually inflow and infiltration. So if you spread that out across the entire state and you look at it from a financial perspective, they're spending $200 million on treating I&I, which is just something that everyone is looking to figure out how to stop. So we will use our chemical grout. That is what is depicted in the yellow part of this graphic around the outside of manholes and pipes. It is a NSF 61 certified material. Basically, it's a two-part expanding chemical grout, a resin hardener. They'll come together and expand to fill the void, displace any unwanted water, and then seal the cracks of the manhole and the pipe. Here's a recent example, not going through all the details of the case study, but in Dunlop, Tennessee, they had some I&I issues. Our team was able to get in there, stop the manholes, leaks in the manholes, such that we only treated 3 structures. But City of Dunlap has started to do some quick math, and they are already seeing 14 to 16 pumping hours per day is the savings. So instead of running almost the entire day long, it's now been cut to single-digit numbers. This is another neat project that we were involved in. This is in Clarksville, Indiana, a suburb of Louisville. And we actually had the city of Clarksville speak on one of our previous webinars. And we only treated 7 manholes. I say only because of the positive impact that it had for the city. So by treating only 7 manholes, stopping the I&I, and you can see some of the before and after pictures, we were able to reduce their pump hours from 49 pump hours a week down to 17. So showing a cost savings of $100,000 a month of just treating these 7 manholes. So now we're working with them to obviously start to look at more within their city system. This is just a graphic to show the reduction, how we were able to reduce by the 65%. So the line graph shows the new cumulative hours compared to the old ones, which are the blue lines. On the last webinar we had, City of Clarksville was very open about the numbers that they were looking at, from $750,000 to a new pump station, $500,000 to reline with CIPP. And obviously we left a little money on the table, but that's all right. We are there to try to solve the problem, what makes the most economical sense. And for $17,000, we were able to treat all 7 manholes. So not every job, not every manhole will have that exact same cost comparison, so please don't get out the calculator and try to figure out a per manhole, because it changes. It all depends on diameter, on depth, on the voids in the soil, and really just the overall condition of the structure and the soil envelope. But regardless, usually it shows out to be much more economical than some conventional solutions. We can also work with age infrastructure, like a brick manhole. And then we have some very neat case studies on box culverts, such as this one in Alabama, where we were able to fill voids, and provide an injectable barrier such that redirect the water. If you see the before pictures, there's no water flowing inside the culvert. Obviously, it's all flowing underneath. Then we were able to reroute the water, so now it's flowing through the culvert like it should and no longer undermining the structure. This is a neat one that we did in Florida, where we lifted a box culvert, a quadruple box, 24 inches, able to lift it 2 feet using our chemical grout. Not only do we do infrastructure from storm and sanitary sewers, we're also doing things like stopping leaks inside tunnels like this church in Chicago. We also will work in the commercial market, increasing bearing capacity, lifting structures, and stabilizing soil. This is an older project, actually done a little over 15 years ago in Kentucky, but the reason to show it is we just recently, in December of 2015, HDR went and surveyed the property and provided us a letter that the elevations have seen minimal to no settlement since our work in March of 2001. So it's neat to see the variety of applications that we've had. And then our crew getting inside boats to work with seawalls and to stop water that is going inside the seawall and pulling out the fines behind the seawall due to rusted out bolt holes or whatever the case may be. And then we work with center pipe to reline the inside of pipe. You can see the picture on the left with a corrugated metal pipe that is deteriorated, but it's still holding its structure, but it just needs to be relined to extend the service life. So we'll fix the invert, and then we will use a spinner, as you see on the picture on the right, to reline in 1/2-inch passes, and we may just do a 1/2 inch if that's all it needs, or we may go up to a couple inches, just depending on the site conditions. Some various jobs, we can use that same technology inside manholes or vertical shafts. This is at the Jacksonville Airport, where we took care of a couple boxes there. And then some just various corrugated metal pipe pictures of various jobs we're using this technology. All the way up to 156 inch. So we will use a spinner for up to 120 inch. Anything beyond that, we will use basically a hand sprayer, hand application. It's the same engineered design mortar, it's just applied differently. This is a neat job that really shows the value of a center pipe compared to conventional solutions. This is a job in Westlake, Ohio, where you see the 280 foot for centrifugally cast concrete, which is center pipe, compared to the CIPP. So not only do you have a price per foot difference, but the significant difference and kind of the game changer on this project is the amount of feet that needed to be treated. As you can see, for center pipe, we only had to do 3,900 feet compared to CIPP, which had to be 7,000 feet. CIPP needs to go from structure to structure, where with center pipe, it can start and stop as needed. And therefore, we don't have to go structure to structure, so you can just treat the areas of immediate need. So it was able to provide the city significant savings, yet treating the areas of concern. So now I'd like to hand it over to John. John Boyles is the president of Inversa, and as we have been kind of going after this outside and inside approach in the marketplace, we were introduced to Inversa and put together a partnership that we are their partner for the 31 states that we cover in the United States, their exclusive partner. And the reason we were so attracted to the partnership is, as we're treating the inside and the outside, working with DOTs and municipalities, there's a component of it that was just not known by the municipalities, and that was to get further upstream to understand what needs to be treated before it becomes a catastrophic failure. So by working with Inversa, they can put together that plan of, let's rehab this now, let's wait a year, or let's remove and replace. So by partnering with them, we were able to provide an overall kind of holistic view for these municipalities, DOTs, and engineering firms that work on asset management. and then work together to provide a solution. So John, I'd like to hand it over to you to really share on the technology. So thank you for joining us today.
Well, thank you very much, Corey. I appreciate the opportunity to be here. So I am the President and CEO of Inversa Systems, and we really are enjoying our partnership with Eurotech down in the U.S. It's helping us gain opportunities in the States which are otherwise very difficult to find through their credibility. So I thought what I'd do today for my PowerPoint would be give you a bit of background about Inversa as a company, talk a bit about the history of the base technology that we've applied, which is innovative on a global basis, talk to you about how we use this technology to look at asset management problems for our clients as a whole, beginning talking about network-wide approaches for typically large DOT type clients, and then I'll show you how we take it from a network-based view down to an asset-specific view, and I'll close with a handful of case studies that we've put together in both the Canadian side of the border and the US side of the border. So Inversa is a Canadian-based company. It's on the far east coast in New Brunswick, Canada, just north of the state of Maine. We say that we are an engineering company first. We provide unique non-destructive testing tools. Our primary markets are offshore oil and gas and civil infrastructure. Although over the last 10 or 12 years we have applied our technology to everything from F-18 fighter jets to Department of National Defense security screening, power generation facilities, refining, but ultimately we found our niches in civil and offshore. So this technology is called backscatter computed tomography, and it's basically a single-side medical CAT scan. And the foundation of this technology actually was out of medical research at the University of New Brunswick, trying to make a low-dose medical CAT scan, with the idea being that a lot of medical patients end up getting secondary cancers caused by too much radiation dose during medical treatment. So at the end of this PhD work, which was taking place in the late 90s and early 2000s, we realized that the PhD was not going to work. But what we ended up coming up with was a way to take a CAT scan image, which would normally require 360-degree access to a human body, and take a CAT scan from a single side. So over the next 5 years, we realized, okay, wow, this means that we can actually take a CAT scan out of a hospital setting and apply it to a variety of industrial imaging problems. So that was the formation of Inversa in 2004 to fundamentally take advantage of a new capability. And in medicine, as many of you would know, a lot of our industrial non-destructive testing techniques originally come from there. Medical ultrasound for fetal monitoring, industrial ultrasound. Medical X-ray, industrial radiography. Medical MRI, and industrial MRI. But the one that never made it out of a hospital was CAT scans, until we were able to find a way to turn it from a 1,000-pound device that you need to lay down and get inside of to a small suitcase-sized device that can still give you the same quality of imaging for qualification purposes. So as an example, I won't go deep into it, but in the offshore market, ExxonMobil has been our largest partner developing this. So we look at things like insulated pressure vessels in service without shutting them down to give wall thickness measurements about the deterioration due to corrosion or erosion. On the civil side of the business, we began by looking at bridge deck analysis. And one day I was in a DOT office trying to figure out how to help them with an extremely large bridge, and one of the engineers gave me an idea and said, John, you know, really, yes, we care about bridges, but roadway culverts are our pain. And I said, well, what do you possibly mean by that? And he said, well, you know, these are the ugly duckling of the industry because they're buried, they're not in the public view, maintenance has historically been not very good on them, and so we end up having these very large diameter structures, in many cases that are actually classified as a bridge, but we don't really know their condition. And the other thing that we know about them is that they're a flexible conduit when they're corrugated metal, and it means that the soil must be intact around them, otherwise it's like an egg, very strong when uniformly supported, but when point loaded, very weak and it buckles. So this engineer gave me you know, sort of a vision that went, holy cow, I think we can really help them. I think we can put together a network-wide asset management program. I think we can find very unique condition assessment data on these structures with a variety of different NDT techniques and show them how to really save money by only doing maintenance and then applying a trenchless rehabilitation strategy with confidence to show them an ROI by, instead of having to dig and replace these structures, being able to trenchlessly rehabilitate them with things like central pipe, which Corey was talking about. So that is how our company got started. All of the patents globally on this technology are owned by our company. We're a very small company, but very unique technology. So there's a few different brands we call it. You may or may not have heard us presenting at a variety of conferences around North America, but SoilSight is what I'm here to talk to you today about, and that's fundamentally our condition assessment package. That's a multi-step approach that allows you to diagnose any CMP structures. So this has been everything from major levee structures for the U.S. Army Corps of Engineers to state-owned storm systems, sanitary systems, and roadway culverts, and really anything that is a composite material where you want to see through one layer and find something else about the layer beneath it. So what drove this industry, in my view, is that a lot of clients, specifically DOTs and large municipalities, are really realizing that asset management is something they've been doing on their pavements and some clients on their bridges for many years, but their underground infrastructure hasn't benefited from that. Much of the underground infrastructure is at or past design life, having been installed mostly between the 1950s and 1970s and having only a 40 or 50-year design life. And so what they really want to do is transition from a reactive to a proactive management strategy, which involves knowing information. So we've chosen to focus on one specific aspect for this PowerPoint, which is really relating to storm, sanitary, and roadway culverts, corrugated metal pipe. So corrugated metal pipe, most of the load-bearing capacity is in the soil surrounding the pipe. And we want to avoid voids forming. And these voids form for a variety of reasons. One is corrosion, through-wall corrosion, so water that does make it into the pipe but then facilitates its way outside the pipe and starts carrying soil away, typically in the haunches first and then expanding around the pipe envelope. Sometimes it's scour and it doesn't even make it into the pipe like Corey talked about and flows underneath it all the way. And other times it can be related to things like embankment failure or potholes holding water and slowly sifting through the soil and then hitting the top of the pipe and washing soil around it. And then sometimes be related to broken storm systems up or downstream that pump water through the ground unbeknownst to the client, and eventually you get a big cavern forming behind your pipe wall. So with CMP pipes, because they're not a fully structural, rigid structure on their own, you rely on the soil. There's a ton of it installed across North America, and it's fundamental that we don't allow water ingress on the outside of those pipes. So we're all familiar probably with this. The classic one that everybody sees failing is the invert, usually beginning due to corrosion and often abrasion accelerating erosive forces. And as you can see here, one that ultimately gets pinched off, and at this point you are no longer able to rehabilitate this. So the trick for the clients is to only spend money on escalating inspection and condition assessment as it's totally justified by the step before, as a proper asset management protocol would show you, and the trick is rehabilitate it right before you lose the option to do so. So the analogy I always give is, I think fundamentally we all understand that if you take a part of your body like your heart, you've got some choices with your heart's health. You can either eat well your whole life and even still have problems, or you can monitor it after a certain age and you can say, look, you know, I want to proactively look after my heart's health. Okay, I'm going to go to the doctor. Well, how do you feel? Okay, well, maybe we should do a blood test. So that's the first level of condition assessment. Oh, you have some high cholesterol. That means you could have other issues. Let's do maybe an X-ray. And an X-ray will look if the area around your heart has maybe any tumors, if everything is where it should be. And then they might say, okay, you know, everything is okay, but you're still showing some signs. We better do a stress test and an angiogram. We're not going to open your heart up and replace it. We're going to simply look if those capillaries and veins and arteries coming into your heart are potentially clogged. If they're clogged, we have relatively non-destructive ways of fixing that for you in the form of a stent. So what we're saying is these pipes are much the same as your heart. So what you should do is you should monitor them. There's protocols that are better than others, and that's what I'm here to walk you through today. And at the end of the day, just before that pipe is going to cause you problems and just before you lose your ability to do trenchless rehabilitation, typically due to deformation, you want to put a smaller amount of money into that pipe, reline it, stabilize the soil around it, and benefit from an entire another design life. Number one, for a lot less cost compared to digging and replacing, but most importantly, our clients are telling us, forget about cost, John, it's the massive disruption to the top side, traffic, buildings, political and social costs. So that's the other soft benefits you have of adopting a trenchless approach. So the way we go about doing this is, as I said, one step at a time. Most people are very familiar with visual inspection. What I can tell you from working around the globe on this is that clients' visual inspection protocols do vary quite a lot. Some are far stronger than others. It varies everything from stick your head into the end of the pipe once every 5 years to some clients every 2 years do full confined space entry and do walkthroughs. So what we did was we decided that one of the biggest barriers to us doing business is we get one of two types of clients. Clients that say, okay, can you give us the best protocols? And we want to be able to undertake the easier steps for ourselves, in which case we are happy to facilitate that with the proper training. 99% of those clients initially want us to enable them, and then they come back and say, you know, you guys really do add a lot of value. Could you do the service work? My company does not want to be a service provider. We want to be a technology enabler. So we work with people like Eurotech who have more staff and more offices to do that on our behalf for the clients. So visual inspection can be simple, but if you know what to look for and you really are trained on what failure modes to measure for, it can be very rich information. So we have built a tablet, or you can use it on a laptop, or you can use it on your phone, but it's a protocol that forces a client or the client's representative or our inspectors through the same rigorous measurement process. So it does not matter who is collecting that data as long as they follow the protocol. But it's crucial that you do or you lose all of the value of the inspection. So we took the 15 US states and top 4 Canadian provinces and mashed together the best visual protocol that we could find. We adopted that into a software tool that will rigorously collect certain information. So that's done as step number 1. Step number 2 is an acoustic inspection. A lot of clients again say, oh, we already do that. And I have yet to meet anyone in over I've been to probably 35 states and all the Canadian provinces that actually do a rigorous acoustic inspection. So again, ours is a patented protocol that's part of the software that forces a certain way of data collection. Essentially it involves a knock test, and we have a specialized tool that can then confirm that. It knocks on every corrugation at 5 relative elevations. Waterline, 45 degrees above waterline. Pipe midline, 45 degrees above midline, and roof line on both sides of the barrel. We are not listening and trying to make a judgment about what we're hearing. We're simply listening to the hammer strike and saying, does hammer strike number 1 sound identical to hammer strike number 2? If not, flag it for follow-up. So the visual protocols and the acoustic protocols are not diagnostic. They're simply anomaly identification is what we say. Then what we do is once we've mapped out all of these anomalies in the software, it will build a 2-scale model of your entire pipe showing you where all the flaws are, and I'll show you what that is in a minute. And then what we say is we're not judging if that knock test sounds hollow or not, just that it sounds anomalous, and then we can drop the radiation scanner, look through the metal wall, and map out all of the soil structure behind, looking for things like rocks or voids or less compacted areas. So we finally have a methodology of screening large quantities of pipe very, very quickly with acoustics and visual, and then going back after the fact only if it justifies it and undertaking a more expensive inspection. So there's an escalation that goes on. So visual inspection, there's a picture of what a tablet would look like. It's typically man entry. We deal with pipes generally 30 inches and larger. The largest pipes we do, although there's no limit to it. I think the biggest one I've personally done is 21 feet in diameter. This is a 10-point visual system, basically following like a PACP type process where 1 is as built and 5 is failed, and then each of the 10 criteria that we physically measure has an auto-generated comment system and then an extra comment system for inspectors to add. So it forces a particular ranking. The acoustic process, again, there's a picture of a ball peen hammer, not showing a specialized tool that we can use. This all leads to inspection with the CAT scan, which as you can see is basically a small suitcase on the left-hand side of the screen. Sometimes it's deployed with a very simple bracing system. So when we get on a plane, all we have to travel with is a little scanner. The wood we pick up on site. We also have rigging that can go off of bolt heads, rigging that can go off of ladders, and rigging that can go off staging. So there's a variety of delivery mechanisms. Setup time typically once the first setup is done is 5 minutes, and a scan is anywhere from 2 minutes to 8 minutes. And what you get is a BCT CAT scan image, backscatter computed tomography. That's the top right. What you want to see is the area that measured no void. That's perfectly compact backfill as you'd like to see. You see it transitioning the void in the middle, and you see entire void on the right-hand side. What clients say about this is it's nice because it's conclusive. For clients that have used ground penetrating radar, it's a blip on the screen that you need a PhD and a postdoc to even make any sense of, and even when they do tell you that, and that's what I did my grad school in, it still isn't very clear. This is absolutely conclusive. So here's what I meant by a pipe map. Now, don't try and squint and look at that. Just sit back and look and know that that top view is one half of your pipe barrel, cut down the center, and the part below it is the other half of your pipe barrel. And the reason why we lay one view over top of the other view is because then you can really tell a story without even necessarily needing to spend the money on a CAT scan what's going on. So what you can tell here is when we overlay this onto your GIS, you know where the pavement is above it. So this particular pipe is about 340 meters long, so 600 feet. There's 4 or 5 lanes of traffic on each direction above this pipe. But what you can tell looking is the black rectangles are acoustic anomalies. So these are areas where our inspector heard quote-unquote hollowness but made no judgment call about it, simply mapped it all out. Black dots are where there's visual indicators per our protocol, and there's a table that goes with this that would say, you know, visual indicator number 1, through wall corrosion 4 centimeters by 5, or rooftop deformation, ovality, whatever those signs are. But when we show this to the DOT engineers and they stand back and go, okay, now, gee, we have all of our problems concentrated underneath the westbound lane of traffic. And if those black rectangles all do turn out to be void, this pipe is in major failure mode. Whereas in this case, the dead center of the pipe, why is that in particularly good shape? And then why are there all of these visual anomalies clustered on the top part of the pipe underneath the eastbound lane of traffic? So there's a lot of information that when we sit down the engineers, we can tell from this. The other thing we can tell is, okay, before you waste the money on radiation inspection, let's presume all of these black dots and black rectangles are void. If they are, what do we know? Well, we know that the majority of them are located in the haunches of the pipe. That strongly indicates a flow-related failure. When we start combining that with the table that says, you know, the first visual indicator is major through-wall corrosion, well, okay, that makes a lot of sense that water is leaking out from within this pipe and washing the soils away. But when you look at the far right of the image, directly across on one pipe section from the other, there's a thin vertical anomaly, black rectangle. And we say, okay, well, why are these ones all across from one another? So basically, standing in the barrel, my left wall and my right wall both have potential voids that stretch above the midline of the pipe. Well, that's not a flow-related failure. Then we start looking in the ditches or looking on the embankments and say, yeah, look, there is a big rat hole hidden by the grass in the embankment. Oh, yeah, there's huge potholing on the surface. Well, water is coming in, hitting the top of that pipe, and washing out a column of soil circumferentially around the pipe. Very different failure mode. We suspect then, knowing that all of those black dots are joint failures because it's cantilevering the pipe. So there's a lot of very rich information that when you know what to look for, you can use this type of view and be absolutely conclusive in what type of rehabilitation planning needs to be done. So this pipe, you know, as long as there's no major ovality happening, is still an excellent candidate for trenchless rehabilitation. Now that we know where those potential anomalies are, before we actually spend the money on rehabilitating it and we want to stabilize the soil, now is the time, once it's justified, to do a radiation scan. So every one of the red dots on the screen is where we took an image. And those images confirm and measure the amount of void. So then we can say to people like Eurotech, here's the final report, here's your confirmed void locations, grout injection port here and here, overflow port there, don't go above this PSI because of hoop stress, blah, 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 a bunch of engineering. We can do a very detailed engineering plan and then go in and rehabilitate this thing as cost effectively as possible. There's no guessing left. There is no how thick should it be. It's all designed. And now the interesting thing is you don't then build a beautiful new pipe within an old pipe only to have all of the soil around it fail anyway, just like that manhole photo that Corey showed. So from that overview of the pipe, just to show you the level of detail we go to, every single section of the pipe from feature to feature is divided up with a detailed table. And what this means is lots of times our recommendation to clients are, guys, you don't need to do anything to this pipe today. Just stop. In 2 years' time, take these same measurements again. We can overlay one set of data on the other and see if things are changing. Maybe a lot of those voids are actually caused by poor construction practices in 1950, and it's not actually intransient or moving. It is okay, but once we know exactly what's wrong, we can compare it from 1 year or one periodic inspection to another. So we measure visual, acoustic, and BCT images. Here's an example, is a neat one. Canada's largest city, City of Toronto. There was a 16-foot diameter pipe, beautiful visual condition. We did acoustics. We had concern on one wall, but nothing that you probably wouldn't rank as sort of a 8 or 9 out of 10, but it was underneath 8 lanes of traffic and 16 feet in diameter. So we figured we should probably BCT it. We BCT'd it and we saw this. It was a 16 by 16 foot cavern stretching from the top of the pipe all the way to the bottom. When we went, we wouldn't have normally done this as part of an inspection, but we went 500-600 feet downstream. Because the stream was so wide and rushing so fast, we didn't see all of that soil building in the outlet pool. It had gone all the way downstream to the first turn in the river and built up on the bank. This actually, because we can tell the direction that the water piped in from, led us back to a broken storm system that was 100 feet away up the road, and all of the storm runoff on the road was going into the storm drain, which had a crack and was pumping through the ground, hitting this culvert and finding its way to the stream. So this was something that probably would have brought down 8 lanes of traffic if it wasn't addressed, but a very inexpensive grout injection job and a full nother design life. So this is just a neat example for a very big asset owner, the value that compares just doing a visual inspection alone, or even in this case, just doing visual and acoustics without doing follow-up. So one of our neatest case studies that's very recent is right now. It's still going on. So phase 1 of this was a study for the New Brunswick Department of Transportation and Infrastructure, which is our word for DOT. These guys have about 10,000 of these large diameter pipes. They said to us, we're overwhelmed. We do a very good job of asset management on pavement and bridges. We don't know what to do with all of these pipes. Can you help us? So we focused on a network-wide approach. We first did a desktop study that said, guys, okay, how do you prioritize these assets today and what data do you have? So a desktop study. Is it age that you use? Is it diameter? Is it risk profile associated with strategic haul roads, in our case being a rural province? Or is it ambulance routes? Or is it detours? Or is it depth of fill? So we do an analysis on all of those on a network-wide approach. We chop that down into, say, as an example, 10%. So over 10 years, you can move it through 100% of your assets. Well, 1,000 pipes is still a big amount of pipes. So how do you go further down the list? Well, you further refine that top 10% in terms of priority based on things like comparative replacement cost to rehabilitation cost. Once we've taken the risk profile of public safety out, then it becomes about money. So we do this to get down to a manageable data set where we go in and we start adding asset by asset detailed information on pipes that we suspect are the highest and most costly. So phase 1 for us in our initial year, which was last year, we did 15 of the large diameter ones. They asked us to do both condition assessment, all forms of it, then write up a rehabilitation design plan if required, and give them an answer. Do we leave it alone and monitor it? Do we dig it out because it's too far gone? Or can we do trenchless rehabilitation? If trenchless, John, would you please write a specification for what that would be? And we want you to do an ROI analysis. And the ROI analysis we kept fairly simple. And what we said was, DOT, you provide us your cost of replacement for both a CMP and bringing up to today's standards. So basically, if you were to replace it with exactly what is in the ground versus what you would do today. So we had 2 numbers given to us by the client, and then we were to do the calculations on the rehabilitation design and show them their savings. This year, we are actually undertaking the rehabilitation. So let me show you about that. So the 15 assets went down to 14 because I think one actually failed before we got there. Of the 14, the criteria we used to drive this was they were large diameter, they were deeply buried because we have a lot of rolling hills, which means their cost of replacement is fairly high, and they have limited deformation so that the majority of the rehabilitation options are open to you. So that was phase 1. Phase 2 was, what are the results? So number 1 was one asset we recommended for replacement. It was too deformed to save them any money on rehabilitation. 4, which they had panicked about and actually thought needed replacement because they did walk through them, hit them with a hammer, and they rang terrifyingly hollow and you feel it vibrating underneath your feet. But when we validated all of that, it was just a little bit of fines that had washed away because all they need is a water stop collar and some riprap. Well, 4 of those are available for continued monitoring. 9 of the remaining ones were excellent candidates for trenchless rehabilitation. So now what we're doing is we're undertaking the rehabilitation. So this involves doing the construction permitting, because this is fairly innovative around here, providing design plans to them, doing all the logistic management, taking care of the material, and subcontracting out the work. So it's more like a design build because they've learned to trust us. And then we have to decide which rehabilitation method is the best and provide all the project management QA/QC. In this case, a lot of the pipes were very suitable for central pipe. And central pipe is what Corey had actually talked about. Very useful in the size of the pipes where CIPP is no longer an option. Slip lining severely reduces your hydraulic capacity, which is usually one of the problems with these older assets to begin with. SIPP is another one that's considered. And CCCP. And CCCP is usually far and away a winner for cost. So we considered all of those different methods. We provided that an ROI comparison to the client, and we ended up being able to save them $7 million of direct cash-on-cash comparison. That's based on replacing it with CMP. It was upwards of $16 million in savings when comparing it to replacement with concrete. This is something that the client signed off on, and here's an example of one of the assets. So this particular asset is one of very interesting engineering sort of criteria. If you take a look at this pipe, you can see from its left wall and right wall, termed south and north view, that most of the problems were concentrated underneath the road. And there was flow-related type failure present, which you can see by most of the black blocks being in the haunches, but there was some around midline too. And those ones are where you really get concerned. This particular pipe ended up, though, only having very minor voids, limited to mostly the valleys of the corrugations. So that means very, very good candidate for fixing whatever joints are separated and then putting a new liner in that pipe so all of the corrosion would no longer allow water to flow behind the pipe wall. So this is what some of the conclusions would be. So on that pipe, there were 17 of these acoustic anomalies, of which we validated 5 as voids and did a grout injection plan for them. The corrosion was bad, but the ovality was good. The deep fill made trenchless rehabilitation an excellent candidate for rehabilitation. And then we did an actual rehabilitation design. And at the bottom of the screen, if you can't quite see it, the ROI was almost $700,000 for CMP and about $1.3 million for a comparison to concrete. So this is one of the candidates we're actually doing a rehabilitation on this summer. This is another neat case study. This is in Edmonton, Alberta, for Alberta Transport, which is one of the largest entities in Canada that uses these CMP pipes. This was a very long pipe under a divided highway. This is one of their crucial highways that connects Fort Mac, which you guys might hear the big fire going on right now, where all of our oil comes from. It was a big pipe. It was about 2.4 meters in diameter, which had very interesting differential failures. So at one end of the pipe, you can see there's a lot of acoustic anomalies. The whole middle section, though, was, I mean, that's almost 200 feet, was okay. And then there were some mid-pipe sections that were failing on the outlet end. So if you look, some of the ovality measurements we made, they were upwards of 20 to 30% ovality on certain sections, but only in certain sections. So we actually were nominated for a minister's award on this pipe because what we found was there wasn't a lot of reason to panic for voids. As you can see, the voids are very small from these BCT images, but they were suffering from very different types of failure. And a lot of it was due to ATV traffic on the embankment, on the outlet end. So we actually were able to show them that of these anomalies that they were panicked about, 30 visual failure points, 30 acoustic ones, we did 44 BCT images in one day. And there's only 3 locations of soil void. So we designed a rehabilitation that for them it was a $16 million dig job because it was so deep and the traffic bypasses, there was no alternatives. So we actually were able to show them that other than a few specific areas, this pipe is in good condition. So why would you dig it out? And they were planning to tunnel bore was their alternative for this one, a huge pipe, which who knows what it would have disturbed on the surface. So we actually were able to show them, look, you can fill these a few voids, you can do some localized repair. From station 0 to 270, you don't need to do a whole lot. You can put in a new center pipe liner or some other liner, which is very cost effective, but on the very downstream end, you need to dig that out because the ovality is too big. But that's on the shoulder. So we can just cut off and connect the new outlet end to that pipe and then reline that so you have one continuous section of mono pipe, so there's no chance of future water ingress. And we were actually able to, I think, save this particular client almost, I think it was $7 million. We're looking at some fairly significant projects for these guys. Just in case there's stormwater people, so I've been talking about culverts, I'll quickly cover a storm system case and then I want to leave time for some questions. This is underneath Canada's largest highway and arterial, the 401 heading into it. This is a city right beside Toronto, our biggest city. 1 kilometer section of storm drain, and these guys had scheduled it for digging it out because they were panicked about what could be under it, and they were going to pave, so they figured they'd dig it out. This was, I think, a $12 or $13 million dig job. We completely avoided the whole thing. We mapped out all of the anomalies. You can see there were some significant voids in these pipes, and there were some unsupported sections, but nothing that couldn't be grout injected. So we designed a rehabilitation plan for these guys. There was 44 anomalies within the 1 kilometer of pipe, and we found 18 large soil voids, but we were able to map them out for them. This is a neat one, maybe more pertinent to our U.S. clients. This is in Louisville. I'm sure a lot of you are familiar, a lot of levee systems. So these are Army Corps assets. We were brought in by MSD Louisville to look at some, I think it was 6 for the most part, and tributaries. These clients had these weird failure modes, which you see here. You can actually see the imprint of the corrugated wall in the top right. In the instance, you can even see the through-wall corrosion. You can see the print of the wall, and what was going on here was they have high clay content, and the soil pulls away from the wall slightly. The soil by the bottom of the pipe buckling up due to buoyant forces and water underneath the pipe. And so you can actually see the entire pipe is slipping out from underneath the embankment, and there's about a 2-inch offset. It floats the pipe and it slides it a little bit. So this was a very interesting, that required a very creative grout injection plan with wall anchors that would help hold this pipe in place. So just sort of shows some of the stuff we can do. On this job, we also found a very unusual thing. They had done some slip lines on these pipes with HDPE, snap tight, and these contractor actually pressure grouted it and failed the pipe. It buckled, and they spent almost a month hand chiseling this out of a 30-inch pipe that was 300 feet long because they couldn't get equipment into it. Fired the contractor, hired a new guy. He did a ton of these pipes for them so fast, they were all impressed. The Corps was happy. We went in and we looked through the HDPE wall, and what you want to see is what's in the top left. The density of the grout, almost similar to the density of the plastic wall, and it's continuous. The right-hand image, we looked way through the HDPE wall, and you can actually see a slight shape of the corrugated wall behind it. That's in the roof. The contractor cheated, and he didn't actually grout inject the pipes. He just capped the head walls, and everybody thought he was so fast and so good. They fired the guy that was doing a good job. He just pressure grouted a little too much on one pipe, and they hired the guy that was a crook. So this was really interesting because the Corps really latched onto this and started to develop different grout standards. From what I understand, it's all stuff that's confidential to us, but this was a big deal for us at the time to find that. So Louisville, here's some summary. There's about 39 anomalies, 14 large voids. And sometimes the voids were even found in the absence of through-wall corrosion, which means that they were pulling away from the wall, like I was saying, and there was a lot of embankment issues due to gophers, I think. There was some sort of critter that dug holes. Yeah, so I guess overall, this is sort of summarizing everything. What we're hearing from clients is they want proactive asset management, but it has to be cost effective because everybody's budget's constrained. We don't mind putting our money where our mouth is and showing them that we will not even charge you if we don't show you and find you savings. So unfortunately for us, most people say, oh, come down and do this one emergency job, and then they start looking at bigger studies. The cost seems prohibitive when you look at one pipe at a time. When you start looking at many pipes at a time, just like pavement monitoring, your cost per lineal foot goes down very, very quickly. So at the end of the day, we end up being able to do network-wide asset management plans driven by very, very data-rich information. We can help the clients facilitate their own data management, do it for them. We work with the clients in any way they want. We can show them how to do it themselves. 99% of the time they want us to use a local contractor like Eurotech, and then we sit in the background and we provide data and engineering support. So that I think that concludes my portion of the presentation, Corey. Thank you all very much for listening. Hopefully it was interesting for you. Happy to take any questions that you guys have, and I think we're still on time to finish on time, so hopefully I wasn't too long-winded. Thank you.
That's great, John. Thank you very much. Very, very insightful. It's always fun to learn more about that, for sure. Now, we do have some questions. I know, let me kind of go through some of them. And Robert, do you have some of those ready to go?
Certainly do. We've had a few questions. I do want to go ahead and remind that if you would like to submit a question, if you look on the webinar dashboard, there's a area in there that has a plus sign called questions, and you can submit your questions there. But I'll go ahead and go through some of the questions that have been asked so far. First one was, is the Inversa system applicable for dam spillway pipes also?
Sure. Can you hear me here okay?
Hear you just fine.
Okay, thanks. So yes, we've used the technology for a ton of different material applications. The majority of what we do is corrugated metal pipe. The depth of penetration, if you're asking about concrete penetration, is about 3 inches. It's not that we can't go deeper, it's that usually it becomes cost prohibitive for the time it takes to do it. So there's sometimes some other techniques that we'll use to combine with it to help us screen where exactly to look. So short answer is yes, it can be applied to dams and spillways. Depends on the material type and depends on the design specifications. What we usually ask the client to do is simply send us a design drawing and we'll tell you whether we'll be able to help you.
Great. What pipe materials and diameters are suitable for this condition assessment process?
Right. So diameter is, as long as we focus on man entry. Typically it's the larger, deeper, more expensive to replace assets. I know that's not always true, but that's where we sort of stake our claim. 30 inches is actually the lower limit of where we typically will crawl through, although there have been exceptions. The scanner can fit, if we want to robotically mount it, down to about 12 to 18 inch diameter pipe, depending on the debris levels. Pipe material, as I said, is 90% CMP, corrugated metal pipe, although we can do any type of plastic pipes. We do composite pipes that are sometimes coated pipes, either bitumen or some other form of coating. From the inside out, we also, with hydro excavation, can do the outside in if you're interested in water piping. And the upper diameter size is there isn't one. It just slows us down a little bit because we have to get on ladders, which you can imagine it usually ends up about 20% longer when we need to do our process on ladders. That said, other material types, our visual and acoustic process can still often work for, whether the radiation scanner works is depth limited. So 3 inches concrete generally, but we can go as far and as deep into corrugated metal and soil as you need. Hopefully that answers the question.
What AMS software do you use?
I'm sorry, it broke up. What type of software did you ask?
AMS.
Okay, so our software is a proprietary one. We've built our own. What it can spit out for data formats is almost anything you want. We keep 5 full-time IT staff, so we get a lot of clients that want us to tie our data into all kinds of different systems like Pontus, all kinds of asset management systems. We can do that. At the end of the day, many clients actually just want us to submit a condition assessment report overlaid onto some sort of GIS like ArcGIS or whatever, and then they want to attach literally a PDF copy and tag it to the particular asset. That ends up being the cheapest and fastest option for them. But I'm not the data guy. If we need more detailed answers, I'll give you to our IT department, and those guys can help you on the data side because I'm not the best one to answer that. Sorry if that's not enough detail, but we've never had a client we can't make happy on the data side.
When is a pipe past the point of rehabilitation?
That's an awesome question. There's 1,000 factors, as with everything in engineering, and what I can do is point out a couple of the most obvious. With these pipes, especially with corrugated metal, their ability to maintain a ring stiffness is crucial. And the more out of rounds, the more ovalized these pipes come, assuming they were supposed to be circular in the first place and not designed to be an arch, the harder it is to get a rehabilitation method that you can argue will be a structural fix. Now, if you don't require a structural fix, ASTM F1216-09 usually gives an option for a fully deteriorated design or a partially deteriorated design. You have to be careful based on the materials you're putting on as a rehabilitation, whether that design parameter makes sense. In many instances, it doesn't. So our civil engineers usually work with the manufacturer to decide, do we need a fully deteriorated design? Because the thing driving a lot of this, I'm sure I've got some engineers rolling their eyes on the phone, is the fact that when you're dealing with a rehabilitation versus a new berry, there's no construction loading. So you don't necessarily, in order to have a reasonable factor of safety, have to have the same original strength as like a directly buried 6-inch thick rebar reinforced pipe. So the short answer is we find, and we would only claim, that something like CentraPipe is a semi-structural, not a fully structural design. The manufacturers, if you spray it on thick enough, will tell you that it can be fully structural. That's not something we normally do, but more importantly, we normally don't find it to be necessary. And our argument is simple. It's that in the case of CMP, it really there is a conduit to allow water to flow through the pipe. And most of your strength after construction loading, so once it's buried, is from the soil arch. So that's why we believe it is so important, regardless of the material type you're putting in for relining, to make sure that the soil is intact around the pipe. And if you do that, then what limits your ability to do the design is things like very bad localized problems. So joints torn apart doesn't mean you can't repair it. It just means you need some localized repair before relining. Ovality, maintain its hoop stress. All of those factors can often be a gate to most.
Seem to be cutting out just a little bit. You may have to repeat
Yeah,
that.
I'll interject real quick here. This is Corey Carlson, Eurotech Holdings. While John's having a little internet difficulty, it actually works out perfect from a timing standpoint for those who need to go. It is noon Eastern, so I want to respect everyone's time and honor your time and allow those who've got to go to other meetings or off to lunch. Thank you very, very much for participating in the webinar today. You're free to go. We definitely will stay on for more questions. Follow us on the normal social media. But the one thing I really want to make sure we mention is we do have a webinar about every 6 weeks or so, and our next one will be on Friday, June 10th at 11 a.m. Eastern. And we work with a PE Rex, and he has put together a report with a third party about how we can increase the bearing capacity of soils using the Eurotech product and methodology. So he will go over the report of how to increase the bearing capacity and really kind of help with estimating, using that to improve soil strength. So with that, those who have to go, thank you so much for participating in the webinar. We will not only see you next month, June 10th, but also anytime between now and then, any problems you have, please reach out to us and we'll look to help you. So thank you. Robert, I'll turn back over to you if you got any final questions for the remaining time.
Okay, great. And John, are you there?
Yeah, I didn't realize I dropped off. Can you hear me now?
Yes, I'm just having a little bit of internet connection, it sounds like. The Okay, the next question. Have you found spot repairs just move the problem down the pipe?
That's another excellent question, and the answer is yes, I have found that, but I have found lots of cases where spot repairs are appropriate. It depends on what the spot repair is, and then taking it in context with the asset as a whole. And so what I mean by that is I do CIPP as well, so sometimes people will go in and they'll do a CIPP repair for water, water infiltration stopping, and then it will squirt through down further. So you see that all the time, not always. When it comes to the larger diameter pipes, spot repair to me means something different. It might be that there is mechanical damage on a joint, in which case repairing that can be sometimes all that needs to be done, and that's not the type of flaw that would propagate further. So it depends on what type of exactly the flaw is, and that's where, again, having somebody knowledgeable that not only can focus on that one flaw, but look at the pipe as a whole, then you can decide whether it's an optimal solution or whether there's some other proactive things you should do to ensure that a couple months later it doesn't recrop up.
For voids where grout is recommended, do you typically drill and inject from inside the pipe, or do you sometimes come from above, say from a road surface through injection tubes?
The answer to that one is you can do both. What we find is depending on the depth of bury and the size of the pipe and your ability to locate the precise void from the surface, it usually ends up being more disruptive, a bit more of a shot in the dark because you can't tell exactly where your injection tip is all the time. Sometimes you can. And from the inside, if it's against the pipe wall that you're trying to inject nearby, it's always better to go from within the pipe because you can put an overflow port. And so you can actually confirm that you're not overpressurizing the pipe. So the design of how, where, and with what material to inject, I typically, but not always, find, if possible, is better to do from within. I feel like you're shooting in the dark from above a lot of the time.
Corey, would there be size limitations as far as injecting from inside the pipe?
From inside the pipe, similar to what John mentioned, we need main entry as well to get inside the pipe, and that's what we'll do. And we'll inject our grout from the inside. It's definitely desirable, so we can see how the grout is coming back into the pipe. We call that a positive seal. So you inject the 5 o'clock and 7 o'clock position of the pipe, the grout expands, and then we'll start to come back in to the pipe, and we can see that positive seal taking place, and then we will just clean up the pipe, knock off some of that grout that has came in to the pipe. And then if necessary, we'll also inject from the surface if we have to, get around the soil envelope a little bit more, or even up towards the surface, depending on what kind of job it is.
This is more of an administrative question. Are participation certificates for continuing education credits? Yes, I'll go ahead and answer that. If we'll be sending out a follow-up email to our feedback survey. Within that feedback survey, there's a question that asks if you were requiring a PDH certificate, and that'll let us know that you need one. Please allow about 5 business days for us to get those back to you. So I'll go ahead and answer that question. The next question is, why can't we do the acoustic test alone?
Yeah, great question, and the answer to that is you can, as long as you have the right procedure and your people are trained. It's not rocket science. We certainly don't make it out to be. We have a specification.
You're cutting out just a little bit again, John. May have to go back, say that again.
Do you have me now?
Yes, go ahead.
Okay, sorry about that. I'm not sure what's going on. We can facilitate a learning procedure so people can do it. I just have seen so many people think they're doing a rigorous acoustic inspection and it be very, very poor. So it's not a matter of intelligence, it's a matter of rigor and procedure. We also have tools that we can help validate what the actual hammer is seeing, and it's a tool that you press against the wall and it simply gives you a void or no void reason. So that's something that we've again designed and patented. So we would have to provide that in order to have the same rigor we would. But if you had a procedure and it was rigorous, we certainly would be happy to show you how to do it. Now, what we will not do, and I was asked this last week, is some people want us to provide our scanners to scan where they tell us and then still ask us to provide a map, which there's a lot of value in. We won't take somebody else's data, put our engineering stamp on it, and then just scan the areas that they think are important. For us, what we're saying is it's that we're trying to assure the QA/QC. So for the right people, certain DOTs will say to us, we just can't do this unless we do it ourselves. We'll say, okay, then we're going to train you. And as long as you follow our procedure, we'll certify it. I have not yet had one, after they've done it, not then go and use a local contractor. So I don't know if that tells you anything about that there is some detail to it, and that most of the DOT clients can't provide the same people to do it in the same way all the time as they can a company that does it every day. So it's like anything, it's just rigorous in training. Hopefully that answers you directly enough.
Have you approached FHWA, Federal Highway System? I'm sorry, I'm not even going to try. The FHWA, there are miles of deep CMP under our nation's highways.
The answer is we're aware of it. We haven't been able to make a high enough level of contact with them, but we'd love to.
And this is the last question. If you would like to submit a question, please go to the questions toolbar within the webinar toolbar. How is this different from using GPR?
Okay, another great question. So fundamentally, it is entirely different. GPR is ground penetrating radar. GPR is a wave that will propagate through a mostly homogeneous soil. It will hit an interface and reflect back, so it's actually a wave. It's a radar antenna that you use. It can get large depth of penetration in the right soil. It cannot pass through multiple materials, so you cannot use GPR inside a pipe at all, fundamentally the physics of it. It won't go through the metal and go into the soil through the void and come back. So GPR cannot pass through air, number one, so you wouldn't be able to find the backside of the void. It reflects entirely off of metal. So where GPR is useful, and we do use it as a tool, would be to look at, say, substrate on your pavement. It could find voids beneath it. It can look at embankments for things like burrowing animals to map out tunnel systems for levees and dikes. We've done that. GPR is used in concrete to locate rebar extremely effectively, but it will only find the first layer of rebar, because after that it reflects off the first layer. It can't get the layer deeper. So the more advanced techniques actually have multiple antennas, but it's very convoluted to try and make something out of the data. So usually it requires a very senior trained geophysicist to make anything out of it, and they still oftentimes can't certify it unless it's the right application. So like every tool, I'm not saying it's not useful. I'm saying you have to use it in the right instances, and it can't be used because of the physics for what we do with the backscatter unit.
Okay, that seems to be it for the questions.
Fantastic, thank you. Well, thank you very much, John, for your time today, and just really enjoy working together. And for all the attendees of the webinar, thank you so much for your participation. We look forward to answering any follow-up questions that you guys have with the survey and getting out the PDHs. And thanks again. Look forward to talking to you on June 10th, if not before then. So have a great weekend. Thank you.